We are still on the graphical representation of motion. In this video, we are going to look at how to describe motion using the three graphs of motion that we discussed in the previous video. And we are going to do that with all the three graphs side by side of each other. So let's begin with when the object or a body is at rest or is stationary. How do we draw a graph of a body at rest or stationary? Let's look at this gentleman down here. He is at rest, and anytime you try to describe his motion or her motion, you realize that at time equals to 0, his displacement is also 0. At time equals to 2, displacement was 0. At time equals to 4, his displacement was 0. Time equals to 6, his displacement was 0. So if you try to plot a graph out of these, you get 0 and 2, 0, 2, 0, 4, 0, 6, 0, 8 onwards. So you notice that your graph is going to be exactly on the horizontal axis. For the sake of this video, we are going to assume that this gentleman has moved and was originally on distance 2 meters before you started to describe his or her motion. Assuming you met the person or the body or the object and it has already covered a distance of 2 meters and you want to describe its motion. Now at time, when time was 0, the displacement or distance of that object was 2 because he's already at a certain distance or displacement. Now time starts traveling from 1, 2, 3 onwards. Now at time t equals to 2, the displacement was still 2. At t equals to 4, displacement was still 2. T equals to 6, displacement was 2. So if you want to plot this on a graph, this is going to give you 0, 2, 2, 2, 4, 2, and 6, 2. And that is this. We have 0, 2, 2, 2, 4, 2, 6, 2, 8, 2 onwards. So if you have to draw a graph that represents an object at rest or an object that is stationary, you are going to get a straight horizontal line that is parallel to the abscissa or the x-axis as we normally like to call them. Now can we plot this on a velocity time graph? Okay, let's see. Now when you check this graph, if you want to find the slope of this graph, we are going to get change in s divided by change in t, and change in s is 2 minus 2. So 2 minus 2 divided by I don't know which one of these you take, but irrespective of which one you take, you are going to get 0 over whatever number you get, and that is going to be equal to 0. So this tells us that our velocity is going to be equal to 0 meter per second. So at 0 meter per second, at velocity 0 meter per second, at time 0 seconds, velocity was 0. At time 2, velocity was 0. At 4, velocity is 0. At 6, velocity is 0 onwards. You can never get any graph out of the velocity time graph for a stationary body apart from what we have done here, and that will be exactly on the horizontal axis. So for this reason, we normally don't draw a velocity time graph for a body at rest or stationary. Likewise, we don't do same for acceleration time graph. So what if the object is not stationary and is moving? In this time around, it is moving with a constant velocity. Moving with a constant velocity means that the rate at which displacement changes is equal to the rate at which the time also changes. So at time 2 seconds, we have displacement to be 2. At time 4, we have displacement to be 4. At time 6, we have displacement to be 6. Now, if you monitor this and this graph is not drawn to scale, but then if this is drawn to scale and you have to plot a graph of this nature, you are going to get a straight line that passes through all the points that you have drawn. And this is for displacement time graph. Also, for displacement time graph, for constant velocity, you get a graph such as this. Now, what about when we are drawing this on a velocity time graph? On a velocity time graph, you are looking at the velocity of the object with respect to time. Assuming at a particular instance, the velocity of the object is, let's say, 4 meters per second. Constant velocity means that the velocity is not changing. So if the velocity is 4, at 2 seconds the velocity is 4. At 4 seconds the velocity is 4. At 6 it is 4 and onward. So by the time you finish, you get a graph that looks horizontal like this, or a graph that is parallel to the horizontal axis or the abscissa. So this is constant velocity for a velocity time graph. If you find the slope of this, you get 0. So for constant velocity, we don't really get a graph for acceleration time graph. You can also get an instance where the displacement of the object will be reducing, or the object is returning back to its original position. And in that case, we normally get a graph that looks like this. It means that the object was at 8 meters. At time 2 seconds, the object is probably at 6. As time gets to 4, the distance have reduced to, let's say, 5. At time 6, the distance is at, let's say, 3 or something like that. So you notice that as time increases, the distance also decreases. For in this case, we can say that the object is returning to its original position. But if it goes beyond the graph like this, we say that the object have passed its original position and it's now traveling in a negative direction. Now it is clear that if you find the slope of this graph, you get a negative slope. So it means that you get a negative velocity. So if you are to plot this, you are going to get your graph to be on the negative side of the graph. So you have -4 and you plot your graph to be something like this. And as we said earlier, we still don't have any graph for acceleration time graph when it comes to constant velocity. And we know from definition that when velocity is constant, acceleration do not come in. Acceleration do not have any business where velocity is constant. At this point, we assume that the body or the object is moving at a non-uniform velocity, which is to say that the velocity with which it is moving with is not uniform. So when you come here, in the initial stages, probably at time 2, velocity was at 2. At time 4, velocity was at 4. But at time 6, instead of 6, velocity is now at 8. So if you want to draw a graph of this, it's very difficult for you to get a straight line, but then it may come through the first 2, but the others would have to curve upwards. So anytime you see a graph of motion where it looks like a curve that goes upwards, this means that the object is moving with a non-uniform velocity. So it is clear that from this point, from let's say time 1 to time 4, so for 4 seconds, the object only traveled this short distance from 2 to, let's say, 3. But then when you check from 6 to 8, from just 2 seconds, the object has traveled from 4 to 8. So it means that here it traveled slowly and here it traveled faster. So it started slowly and increased upwards. So this means that the velocity here was small, then the velocity started increasing because the change in displacement with respect to time here was small and the change in displacement here is greater. This means that we have on the velocity time graph, we are going to start with a smaller velocity and the velocity is going to keep increasing, whilst time also increases. So as velocity increases and time increases, we get a graph that looks like this. So for a constant, for a non-uniform velocity on a velocity time graph, we get this. On the graph, you can now find your slope and the area under the graph to get the acceleration and the total distance traveled respectively. Now this, we can find the slope. If you find the slope, you get acceleration. Assuming you find the slope of this, you get acceleration to be 6, and assuming that will be 6, we get our graph to be horizontal or parallel to the horizontal axis. You can also get a graph like this where the object moved faster, then it slowed down. Here it moved faster and slowed down, but then the other graph, it moves slowly and then sped. It moves slowly and then it started moving faster. So this one is moving faster and now moving slower. But in the other graph, which was like this, it moved slower and at this point it moved faster. What if this time around the object was returning back to its original position as we did in the uniform velocity? It is returning, but then during the return journey, the time it used to cover each distances was not constant. So we said that we don't have a constant velocity. So this one, when you plot a graph like this, is going to give us something that looks like this. It means that it started from a greater distance and then the distance started reducing, which is to say that it is returning to its original position. Now if that happens, it means that we are going to get a negative velocity. A negative velocity means that we are going to have our graph at the negative side of our plane. So if you plot these graphs, you get the graph looking something like this. This can also give you a velocity time graph which also looks like this, though in the positive region, but this will give you a negative slope. So anytime you see this, it is correct. Anytime you see a graph that looks like this, they are basically the same though. This and that graph, when you watch, they are basically the same. Only that this time here we are drawing it at the negative side and here we are drawing it at the positive side. But both of these graphs would give and should give us a negative value. And if you are to plot this on an acceleration time graph, since the slope is going to be negative, it means that we have negative acceleration. And negative acceleration means that we're plotting our constant acceleration. This time we said it was 6. Our acceleration is going to be on the negative side of the graph, which is parallel to the horizontal axis. So for the sake of our level, and for the sake of kinematics as we are studying, all the equation of motion and everything we are doing is focused and is true when acceleration is constant. So for this reason, we don't want to go beyond a constant acceleration. We can get other graphs that has to do with increasing acceleration or decreasing acceleration or whatsoever, but then we are interested, or we want to limit ourselves to acceleration being constant or constant acceleration. So we won't go beyond this, and this is where we will end the graphs of motion and start looking at examples.